Hello everyone, let's analyze. So today we're going to talk about series, but before we get deep into the details of series, let's talk about Zeno, specifically Zeno's dichotomy paradox. Zeno claimed that motion was impossible, and if motion was impossible, whatever motion we perceive must be just an illusion. And he gave the following example. He said, suppose you start at 0 and you want to reach someplace 2 units away. Well, first you have to get halfway there, which means you travel to 1 unit. And then you would travel half the remaining distance. That takes you to 1.5 units from where you started. And then you would travel half the remaining distance, taking you to 1 3/4 from where you started. But then you had to travel half the remaining distance and half the remaining distance again. Well, if you keep traveling half the remaining distance over and over and over, will you ever get there? To complete the trip requires completing infinitely many sub-trips, where each of these sub-trips are positive lengths. So can the trip be completed? Can we sum infinitely many positive values and obtain a finite value? Right, that's one way to look at resolving this paradox. Well, in order to travel the whole way, our total distance would have to be the sum of 1/2 to the kth power as k went from 0, 1, 2, 3, 4, and on forever. Is that total distance a finite number? We're adding infinitely many positive numbers. Can infinitely many positive numbers sum to something finite? Well, of course, when we see an infinity, we know that there's a limit hiding somewhere. So, what do we mean when we say an infinite sum? Well, when we say an infinite sum or a series, and that's what a series means, it's basically an infinite sum. An infinite series is, well, an infinite sum, and it's a sum of terms that are indexed by some number k. And k sometimes starts at 0, 1, it could start at 2, it could start at 7. But what do we mean if we say that this infinite series is something? Is it anything? Is it a number? Well, we say that a series converges if the partial sums, defined as the sums from the first index to n, if those partial sums are themselves a convergent sequence. Well, if we say a series converges if its partial sums converges, well, the partial sums is just a sequence of numbers, and we know how to deal with sequence of numbers. We've been dealing with it for, well, a few weeks now. So in fact, a series, or the convergence of a series, is really a question of the convergence of a sequence. So nothing new. I suppose we could stop here then. Well, perhaps there's a few more, or a bit more detail about analyzing series, which we could say is a particular type of sequence analysis. So let's talk about an example. Recall that from a previous lecture, we considered the sequence Sn, whose nth entry is the sum of 1 plus 1/2 plus 1/3 plus every reciprocal of integers up to n. Well, that's actually a partial sum, right? It's the partial sum of 1 over k as k ranges from 1 to n. Now, we demonstrated, if you recall, that the sequence of partial sums were unbounded. And of course, if a sequence is unbounded, then it can't converge because convergence implies boundedness. In particular, we showed that the 2 to the n entry of my sequence was 1 plus n over 2. And well, 1 plus n over 2 can get arbitrarily large. So there's no upper bound that I can give for my sequence. And if the sequence of partial sums is unbounded, then the sequence diverges. And if the sequence of partial sums diverges, then by definition, the series diverges. And this series is known as the harmonic series. It's a well-known divergent series. Let's take a look at another example. Let's consider the sum of r to the k as k ranges from 0 to infinity. And in this case, the absolute value of r, we'll say, is strictly less than 1. All right, hopefully you can see why, if the absolute value of r was greater than 1, or 1, right, then this series would have no hope of converging. So we'll consider the case where the absolute value of r is strictly less than 1. This is known as the geometric series. So let's consider the partial sums, which is the sum of the terms from k equals 0 to n of r to the k. Right, so r to the 0 plus r to the 1 plus r to the 2 plus r to the 3 up to r to the n. So we can write it this way. And then we're going to multiply by 1, but with style and purpose. Specifically, we're going to multiply by 1 minus r divided by 1 minus r. Now, of course, we know we're not dividing by 0 there because r in absolute value is strictly less than 1. Now, if we distribute the numerator of our 1, that is 1 minus r divided by 1 minus r, right? Well, first we would multiply by 1, which is just to get that same partial sum, minus the product of multiplying each of these terms by negative r. So 1 times negative r is negative r times negative r is negative r squared, right? R squared times negative r is negative r cubed, so on and so forth. And you'll see the cancellations that we get, r minus r squared minus r squared. Hidden in the dots is r cubed minus r cubed. We have rn minus rn, and the only terms we're left with is 1 and minus r to the n plus 1. So we got a lot of cancellations. So we actually have a simplified expression for our partial sum that doesn't require a sum at all. So then now our task is to take the limit as n goes to infinity of our partial sums. And so let's do that. Since my partial sums is equal to this term, I need to take a limit of this term. Well, I can separate this fraction at the numerator. You get 1 over 1 minus r. Now notice this is constant with respect to n. And this term. Now that equals 1 over 1 minus r, because again this is constant with respect to n. I just get the constant. And as n goes to infinity, this numerator goes to 0 because again r is less than 1. So I'm left with just 1 over 1 minus r and the limit of my partial sums. And because my partial sums converge, the series converges. Not only that, I actually get a value for my series, 1 over 1 minus r. This resolves Xenos' paradox, because Xenos' paradox required us to add 1 over 2 to the k, which can be thought of as half to the k, and of course half is less than 1. So the distance traveled, 1 over 1 minus half, 2. Well, of course the distance traveled is 2. There's really no contradiction at all, we can add infinitely many positive distances to travel and get a finite number. So let's consider another example, since the previous one was so much fun. Let's consider the series 1 over k times k plus 1 as k ranges from 1 to infinity. Well, to consider the series is to consider the convergence of the partial sums. So let's look at the partial sums. Right? It looks just like the series, but we're going to truncate our infinite sum at n. So we have n terms. Now we're going to do a little bit of rearranging by dusting off our partial fraction expansions. 1 over k times k plus 1 is the difference of 1 over k and 1 over k plus 1. Of course, you could put this over a common denominator and deduce that you get this out. Well, now that we have a minus, maybe we have some cancellation like in the previous problem. Let's take a look. Let's look at this partial sum term by term. Well, when k is 1, I get 1 over 1 minus 1 over 2. And when k is 2, 1 over 2 minus 1 over 3. When k is 3, 1 over 3 minus 1 over 3 plus 1, 1 over 4. So forth and so on. Right? When k is n minus 1, the second to last term in my partial sum, 1 over n minus 1 minus 1 over n minus 1 plus 1. 1 over n, in other words. And the last term in my partial sum, 1 over n minus 1 over n plus 1. And now you see my cancellations. Negative half plus half. Negative a third plus third. Negative a quarter plus a quarter. That quarter is right here in the dot, dot, dot. You can't see it. Just like there's a negative 1 over n minus 1 hidden in the dot, dot, dot that cancels this term out. And we see these terms are canceled out. So after my cancellations, I'm left with 1 minus 1 over n plus 1. Well, now that I need to take the limit of Sn, well, that's just the limit of 1, which is, of course, 1 as n goes to infinity, because as n goes to infinity, 1 is 1. 1 doesn't really care what n is doing. 1 over n plus 1, we have a denominator that gets arbitrarily large. Therefore, 1 over n plus 1 converges to 0 because the numerator is constant. So we just get 1. So we have another convergent series, and specifically converges to 1. So because a series converges when the sequence of partial sums converges, and we know that a convergent sequence is equivalent to a Cauchy sequence, then the sequence of partial sums must be Cauchy. And if the sequence of partial sums are Cauchy, we could deduce that an infinite series converges if and only if, for any epsilon, there's some natural number n, so that if n is greater than n and p is any natural number, or 0, then the sum of terms from indice n to n plus p is less than epsilon. And again, that comes by just applying the Koshi criteria to the partial sums. So it's a pretty straightforward application, so I'll just leave it for you to do in your homework. A corollary to that, and something that I think is fairly obvious, that if a series converges, then the terms in the series, that is the numbers being added, must converge to 0. Right? They must converge. Because if it doesn't converge to 0, then at some point it stays far from 0. And if it stays far from 0 for infinitely many terms, then I'm adding something potentially infinite over and over and over. And there's no way that I could ever get a finite outcome. out of such an infinite sum. But the Koshi criteria actually makes it fairly straightforward to prove. If the series converges, then the Koshi criteria applies. What is the Koshi criteria? Well, it was on the previous slide, we just write it down. All right, for every epsilon, there is a natural number n, big N, and if little n is greater than or equal to big N, and p is some non-negative integer, then the sum of an plus 1, all the way through an plus p in absolute value is less than epsilon. Right, we just wrote down the Koshi criteria, which is true. And remember, p is any non-negative integer, so suppose p is 0. Right, 0 is greater than or equal to 0, so that works. Well, in that case, this sum here is just one term, an. Which is, of course, an minus 0, and that's less than epsilon. That implies that an converges to 0, because that's the definition of convergence. All right, for any epsilon greater than 0, there's a natural number n, such that if n is greater than big N, the absolute value of an minus my limit, 0, is less than epsilon. Right, we've proven precisely what it means to converge. Okay, now let's discuss absolute convergence. We say a series converges absolutely if, and only if, we say this, the series of absolute values of the terms converges. Now, if a series converges, but the series of the absolute value of the terms diverges, then we say that the series converges, but only conditionally. So absolute convergence is a stronger criteria. Absolute convergence implies convergence, but of course not the other way around. Now the proof of that theorem is merely an exercise in triangle inequality, and I'll leave that for your personal enjoyment. So one of the most useful tools for analyzing a series is to compare it to a series for which you know the behavior. For example, a series that converges or a series that diverges. So let's consider two series, an A series and a B series, where the B series has terms that are all non-negative. Well, if the B series converges and the A series has terms whose absolute value is bounded above by the corresponding terms in the B series, for every n greater than some integer big N, then the A series converges and converges absolutely. Now, if the B series diverges, however, and the absolute value of the terms in the A series is greater than the corresponding terms in the B series at some point big N and for every term after, then we say that the series of absolute values of the A series diverges. So let's prove the statement. First, let's suppose that the hypothesis of the first bullet is true. That is, the B series converges. So it's equal to some number B, which is less than infinity. That less than infinity is really a shorthand that you often see sometimes. If a series is written to be less than infinity, what is meant is that the series converges. It equals to some finite number. And in this case, we're going to call the finite number B. Now let's let an be the partial sum of the absolute value of the terms in the A series? Well, I claim that A little n is less than or equal to A big N plus B for every n. Well, why is that true? Well, suppose little n is less than or equal to big N. Well, sum of these terms summed is going to be less than the sum of all of these terms because the terms being summed are non-negative. And of course, an is less than an plus b because b has to be greater than or equal to 0 because all of these terms are greater than or equal to 0. Now suppose n is greater than big N. Well then, the first n terms, big N terms, is exactly equal to this by definition. And then the remaining terms, right, is a subset of these terms, which when summed is less than if I sum up all the terms because each term is non-negative. And of course, those sum to b. So a big N plus b is an upper bound of a little n for every little n. Right? We can bound the partial sum. And since a little n is a monotonically increasing sequence and it's bounded, a little n must converge. Meaning that the A series not only converges, but it converges absolutely. And the second bullet follows directly from the first. Because if the second bullet is false, then it immediately contradicts the first bullet. Because suppose the B series diverges, but the A series converges absolutely. Well, if the A series converges absolutely, then by comparison, the B series would converge. Which contradicts our supposition that the second bullet is false. It can't be false. So let's use the comparison tool to test this series of terms 1 over k squared. Now, our plan of attack will be to compare it to the series 1 over k times k plus 1, which we showed just a few moments ago converges, right? Which again we say, therefore the series is less than infinity. Again, that's just a shorthand way of saying that this series converges. But before we compare, a little rearranging is in order. So the sum 1 over k squared as k goes from 1 to infinity is the first term, which is 1, plus all the remaining terms. So starting at k equals 2 onwards. And well, I can actually re-index that part there to be from k equals 1 to infinity, and just replace k with k plus 1. So of course when k is 1, I get 2, the first term here. When k is 2, I get 3, which is the second term here, and so forth. Now, why did I re-index in this way? Well, that's a really good question. I'm glad you asked. I did it because k plus 1 is greater than k. So if I multiply both sides by k plus 1, I get k plus 1 squared is greater than k times k plus 1. So if I take the reciprocal of both sides, I get 1 over k plus 1 squared. The terms in this series is less than 1 over k times k plus 1. The terms in this series. And of course, the terms in both series are positive for all k. So by the comparison test, because this converges, then this converges. And since this converges, so does our original series which is just one less than this. And so we've proven that the series that we first considered converges. Another useful test to put in our toolbox is the ratio test. So we'll consider a series, this time of non-zero terms. If there exists a number q strictly between 0 and 1, and some natural number big N, such that the absolute value of the ratio of consecutive terms is less than or equal to q, so long as those terms come after big N, then we say the series converges. Now, if, however, there's some natural number n, such that the absolute value of the ratio of consecutive terms is greater than 1 for every term past big N, then the series diverges. So let's prove this result. Suppose the hypothesis of the first bullet holds. Then I can choose little n to be equal to big N. And a big N plus 1 would be less than or equal to q times the absolute value of a big N. And it would be true if little n is big N plus 1. That is, a n plus 2 would be less than or equal to a n plus 1. And of course, I got a bound for a big N plus 1. It's q times the absolute value of a big N. Well, I could carry on that style of analysis, and a times n plus r would have to be less than or equal to q to the r power times a to the n. I'm sorry, a subscript n, that is. Not to the. Well, I'm going to write that in a peculiar way. I'm basically going to multiply by q to the big N and divide by q to the big N. Now, suppose k is big N plus r. So I'm going to call this exponent here k. Right, because here r, right, can be kind of any integer that ranges from, right, 1, 2, and onward. So if k is n plus r, k is greater than or equal to big N. And ak, right, which is this term, is less than or equal to this. I'm just replacing n plus r with k, because, well, that's what k is equal to. So now, let's take them and let's sum them up. Because, right, we want to show that these, when summed, converge, right? That would give us our absolute convergence. So we're going to compare it to these terms. Well, notice the only term that has a k is this one, meaning this can be factored out. So I factor it out. And this series here is a geometric series. Why? Well, because q is strictly between 0 and 1. In other words, the absolute value of q is less than 1. So this geometric series converges. And of course, this is just some finite number. So by comparison, this series not only converges, but converges absolutely. So we've proven the first bullet. The second bullet, well, if the hypothesis of the second bullet is correct, then for every n past big N, an plus 1 is greater than or equal to an absolute value. In other words, the absolute value of my terms are monotonically increasing and away from 0, right? They're bounded away from 0. So if these terms are monotonically increasing and bounded away from 0, well, then they can't possibly converge to 0. And these terms have to converge to 0 if I have any hope of an infinite sum of them converging to some finite number. So the series diverges. The root test. So this is the last arrow in our quiver. Again, we'll consider a series. And if there's a q greater than or equal to 0, but strictly less than 1, and there comes some natural number big N, such that the nth root of the absolute value of an is less than or equal to q, for every single little n greater than or equal to big N, then the series converges absolutely. If, however, for infinitely many little n, the nth root of the absolute value of the nth term is greater than or equal to 1, then we say that the series diverges. So how would we prove this? The proof is actually quite nice. To prove it, I will assign you homework. It'll be fun. That's it for today.